Okay, calculus friends, here our first two examples are from yesterday, right? We talked about how we find the derivative of an inverse, right? So notice the notation, this notation here, this is your derivative notation, right? This means take the derivative with respect to x, and this here is your inverse notation. And there's a formula for that, so let's write down what the formula is. The derivative of an inverse is 1 over the derivative of the function's inverse evaluated for that x term. Okay, so that's the formula that we're going to do. First of all, our first thing we have to do is find the y value, right? Find x value, right? Because this, for our inverse function, this is a y value. Because the y value of an inverse is the x value of the function, right? And the x value of a function is the y value for the inverse. That's how inverses work. They switch their x's and their y's. So the first thing we're going to do is we're going to find the x value for the given coordinate, in this case 1/2 it looks like. And then after that we're going to take the derivative and evaluate it at that point. Okay, and then the third thing that we do is we reciprocate it. Okay, so there's 3 steps to finding these derivative of an inverse problems. We find the x value, and then we take the derivative from that x value, and then you reciprocate. So let's see, we have the function sine. We have the sine function, and we want to know what is the derivative of the inverse of sine, or arc sine of 1/2. Okay, that's what we're trying to find here, is what is the derivative of the arc sine at 1/2. So remember, this is an x value for your inverse, so it's a y value for your function. So we want to know at what angle is the sine 1/2. Right, that's what this is asking us. At what angle is the sine equal to 1/2? And if you know your unit circle, which hopefully we do, we know that happens at pi over 6. Pi over 6 is where the sine has a value of 1/2. So now we're going to evaluate the derivative. So we have to figure out what is f prime. So if sine is our function, what's the derivative of sine? That is cosine. Okay, so we take the derivative of cosine. Now we're going to plug in pi over 6. What is the cosine at pi over 6? Right, that's what we're figuring out next. The cosine of pi over 6 is root 3 over 2. Okay, so the cosine at pi over 6 is root 3 over 2. That's our second part. We have evaluated the derivative at your x value. And the third part is to reciprocate. Okay, so our actual derivative of our inverse of 1/2, right, the derivative here is 1 over root 3 over 2. Now, unfortunately, you're not going to see it like that represented on a multiple choice test. They're going to want you to multiply by the reciprocal and get 2 over root 3, right? That's what it means to reciprocate, is to make your numerator your denominator and your denominator your numerator. And then we do one more step called rationalization, where you multiply by root 3 over 3. And this means we no longer have a radical in your denominator. We have the normal number 3. So this is the derivative, right? The slope of the tangent line to the arctan at positive 1/2. Okay, so here's another trig one. G is the tangent function. So we want to know what is the derivative for the inverse tan function evaluated at 1. Okay, so first of all, this 1 is an x value for inverse, which means it's the y value for your function. So we want to know at what angle is the tangent have a value of 1. Okay? So once again, if you know your unit circle, that happens at pi over 4, or 45 degrees. Okay? The tangent has a value of 1 at 45 degrees, because tangent is a ratio of sine over cosine. So if it's going to be 1, it has to be the same number over the same number. So root 2 over 2 over root 2 over 2. The tangent is 1 at pi over 4. Okay, so now we have to take the derivative of tan. So have you memorized derivative of tan? All right, so good. The derivative of tan is secant squared. Okay, and now we're going to evaluate secant squared at pi over 4. Okay, so if you haven't memorized it, that's fine. Right? We need to understand that the secant is the reciprocal of what other trig? The secant is the reciprocal of cosine. So the cosine at pi over 4 is root 2 over 2. Okay, the cosine at pi over 4 is root 2 over 2. So then what's the reciprocal of root 2 over 2? Right? Let's come over here and do that. So root 2 over 2, we have to reciprocate it, which means we get 2 over root 2, right? And then we're going to rationalize, which means we multiply top and bottom by that denominator, which is a radical. Okay, right? We are rationalizing. So we get 2 root 2 on top, and on the bottom we just get the number 2. And can we simplify that? Yes, we can. So the secant at pi over 4 is positive root 2. Okay, so that's what I'm going to plug into my secant, right? This says to square the secant value. Right? It says secant squared at pi over 4. Well, the secant of pi over 4 is root 2. So when I square root 2, I get positive 2. Okay? But I'm not done, right? That's just the second part. That's finding the value of the derivative. So our third part is going to be to take its reciprocal. So 1 over 2. The derivative of tan, g inverse, I guess, g inverse at 1 is going to be 1/2. Okay, so there's 3 steps when we're finding the derivative of an inverse. Right, first we have to find the x value for your function that goes along with your given y value. Okay, this is a y value for your function, so we figure out what is the x value there. And then we take the derivative of your function and we plug in that x value that we found. And our last step is to take the reciprocal of that evaluated derivative. Okay, 3 steps anytime we want to do an inverse of a derivative question. Okay, so the rest of this is a rule called L'Hopital's rule. And it's where if you plug in your function, we get 0 over 0 or infinities over infinities. Okay, so we're going to plug in your value every time to check, to make sure that we are able to use L'Hopital's rule. Because if we get anything other than 0 over 0 or infinity over infinity, then we can't use this rule, which says that the limit of your function is the same as the limit of the derivatives. So we're going to be taking the derivative of the numerator and the derivative of the denominator until you no longer get a 0 over 0 or infinity over infinity form. Okay, so let's see how this works. Now this is the formal way of doing it, and this is a true statement. If we have an FRQ on your AP test, this is what you have to do. Okay, so we can take the limit of the numerator and the limit of the denominator separately. Right, so this is how we are going to evaluate that we are actually able to use L'Hopital's rule. Okay, so you take the limit of the numerator and you take the limit of the denominator separately. So we do this by direct substitution. What happens when I plug negative 4 into x? Negative 4 cubed is? Good. Negative 64. Negative 64 plus 64 is 0. Okay, and then in the denominator, when I plug negative 4 into here, negative 4 plus 4 is 0. Okay, so we do in fact get the indeterminate form when we plug in negative 4 into our numerator and denominator. Okay, so we can say that we can use L'Hopital's rule which says, let's take the derivative of our numerator and our denominator. So we're still taking the limit as x approaches negative 4, but what is the derivative of x cubed plus 64? 3x squared, right? The plus 64 derivative is 0, so we don't have to worry about that. And then on the bottom, what's the derivative of x plus 4? That's just 1, right? The derivative of 1x is 1. If it were a 5x plus 4, the derivative would be 5. So the derivative of the bottom is 1. All right, now let's plug in negative 4 again. What do we get? Negative 4 squared is positive 16. 16 times 3 is 48 divided by 1 is just 48. So the answer to this problem is 48. Okay. Now, the beginning of school, we would have factored, right, both the top and the bottom, and we would have canceled out things that can cancel, and then you plug in the number in again. Okay, so this is another way to do it non-algebraically using calculus and derivatives. Okay, so remember, it's an indeterminate form. So we're trying to figure out what is the limit as x approaches infinity. Okay, so if I were to take this and plug it in, what's infinity squared? Right, infinity. And what's infinity squared? Infinity. So we have infinity over infinity. That's one of your indeterminate forms. So we can use L'Hopital's rule. Okay, so the limit as x approaches infinity of, what's the derivative of the numerator? 6x minus 5 over, what's the derivative of my denominator? 2x. Okay, all right, let's plug infinity in again. What's 6 times infinity? Infinity. 2 times infinity? Infinity. So we're going to do it once more. Okay, as long as we get infinity over infinity, we are not done L'Hopitaling, right? We're not taking the derivatives. So then I have the limit as x approaches infinity of, what's the derivative of 6x minus 5? 6. And what's the derivative of 2x? 2. So 6 divided by 2 is 3. And the answer is 3. Okay, now in pre-calculus, we learned that this was a horizontal asymptote, and our function is neutrally heavy, right? X squared over x squared. So that means we look at the coefficients, 3 divided by 1. The horizontal asymptote is 3. All right, so that's the y value that this function is trying to approach as x's get infinitely large. Okay, so sometimes that works out both ways from calculus and pre-calculus. And other times, it does not. Okay, e to the infinity power, infinity. Infinity squared, e to the infinity, infinity, right? So this is infinity over infinity. We can use L'Hopital's rule to figure out what the limit as x approaches infinity is going to be, right? What is that horizontal asymptote of our actual equation? Okay, and e, what's e to the 3x's derivative? E to the 3x times 3, right? So our e derivative is itself times the derivative of your power. Okay, so this is e to the 3x times 3. And on the denominator, 2x plus e to the x. Okay, the derivative of e to the x is itself, right? E to the x times 1, basically, which is just itself. Okay, all right. Still have e to the 3 infinities, right? 3, that's still infinity. On the bottom is still infinity. So as long as we get an indeterminate form, we have to take the derivative again. So what's the derivative of 3e to the 3x, right? That's how we're going to write this. The derivative of 3e to the 3x is 3e to the 3x times 3, right? We're multiplying it by another 3. So we don't mess with our initial e to the power, and you multiply it by the derivative of your power. But on the bottom we get 2 plus e to the x. Okay, what happens when we plug in infinity? We get infinity over infinity still. All right, let's take L'Hopital's rule again. The limit as x approaches infinity of 9e to the 3x, right? 3 times 3 is 9, times another 3. And on the bottom, what's the derivative of 2 plus e to the x? It's just e to the x. Okay, so this is getting kind of annoying here, but that's okay. Let's simplify. This is 27e to the 3x divided by e to the x. Okay, so what can we cancel out? So this is 27 e to the 2x times e to the x, right? That's something we can do with our 3x. Yep, so e to the 3x is 2x plus 1x. Okay, and I do this so that I can cancel out my denominator. But still, if I take the limit as this approaches infinity of 27e to the 2x, what do I get as my answer? Infinity. Okay, so my answer is infinity, which means as x's get really, really large, the y values get really, really large also, right? It's exponential growth. So we do not have a limit. It goes off to infinity for this problem. I know all that work for an infinity answer, but sometimes, right? It's practice with your derivatives. So every time we get infinity over infinity, you take the derivative again, and so you no longer get infinity over infinity. Okay? Your infinity answer is a perfectly fine answer. Okay, so here are our last 3. When we plug in infinity into natural log, we get infinity over infinity, and then we take its derivative. So the derivative of natural log is 1 over x. So when we plug in infinity, 1 over infinity is 0, right? It gets really, really close to 0. So then 0 divided by 2 is still 0. Okay, 5 and 6 are done similarly. When we plug in the value, we get 0 over 0. So we take the derivative and then evaluate it at their points, okay? Because the derivative of your denominator is just 1. Okay, so there are your 2 answers for the entire thing. Okay, so we have to have an indeterminate form before you can use L'Hopital's rule. Okay, so always check to make sure we get 0 over 0 or infinity over infinity before we take the derivative and proceed. Okay, good job. Have a swell day. We'll see you next time.